We're going to do a quantum spin lecture, and this topic is very important. Fundamental is of fundamental importance. It's called Rabi oscillation. Who among you have heard of this? Rabi oscillation.
We did the lab last week.
Okay, but prior to this course, no, only you, right? How about you? What? You have not? You have, okay. Yeah, this is introduced for the first time in quantum physics course, quantum physics class, maybe the junior year. And it seems all very simple, but actually there's a lot to it. And this is going to be the foundation for quantum information processing. So today's lecture is very important. So I hope we can all pay close attention. All right. So let me start with where's my, okay, here. All right. Let me start with this. We know in one of our quiz, we have asked this question. We have asked this question. How many qubits are here, right? Who remembers the answer? Zero. Yes. And I said the reason is because the key, huh?
It's not closed.
Yes, the key is closed system. A qubit, to be used as a qubit, you must have a closed system. That means as you pump, it needs to transition continuously between the two specified states, 0 and 1. Okay? If it relax to this state. If it's excited to this state. It needs to be a closed system. But in this case, for the MV sensor that we have two states that are physically distinguishable because we know the spin configuration is different, right? This is this. Okay, so they are physically distinguishable, yet the energy is the same. So when you give an excitation, you'll go to either one of the states. If there's only one photon, it could go to this one or go to this one, or even a superposition. When it relaxed, of course, you'll get here. So it could be like you first go to this state, and then you're driven back, and then you go to the next state. Okay. Such a 3-level system is interesting on its own, but it's not good for qubit applications. Therefore, we need to do something to make MV center into an MV qubit. All right, so this is MV center. This is just MV center, and this is an MV qubit. Yep. Okay. So the method we're gonna employ is something called Zeeman shift. Zeeman shift. Who has heard of this? Zeeman shift? Everyone? Okay, great. We're gonna use Zeeman shift. How does this work? It's pretty simple. When we we're considering the NV center electronic structure, all its levels are degenerated, right? And then there was a splitting. Yeah, there was a splitting. This is called zero field resonance, or zero field splitting, and this is called zero field splitting. And the magnitude is 2.875 gigahertz. You remember this? The cause of this, you see, the n equal to 0 level is not shift. Only the n equal to plus minus 1 is shift. And the reason for this is because the Coulomb interaction between the two electrons. Yeah, so we talk about this. Now, these two states are degenerate. So we need to think of something to separate them. And the method we're going to use is called Zeeman shift, which is to simply apply a magnetic field around the MV center, around the sample. And the field will split this two level up and down. The plus one will be in a higher energy state, and the minus one will be in lower energy state. Okay? The gap here will be proportional to the electron magnetic field energy. Okay, so we know the magnetic field the magnetic field interaction is this, right? So this will be proportional to the electron magnetic field energy. So you can imagine you have a basic unit of the magnetic moment, which is the Bohr magneton. And of course, you're going to have B, and since this is a dot product, so that's B in the projected direction. Okay, so just U and B. And G here is a dimensionless vector. It's just a geomagnetic ratio. And it takes the value of around 2 point something, 2.0 something, but you can just take it as 2 for electron. All right. What else? Is this all? Is this the splitting we have? Oh yes, there's hyperfine structure, but we will talk about that later. This is the result for a single electron. Okay? But we have the two electron state, right? Because we have up, up, and down, down, right? And for this case, up and down, the energy canceled, right? One has a positive shift and the other has a negative shift, so it cancels. But for this two, they add. All right, so we should have a factor of 2. Oh, by the way, I'm sorry. There's one more thing. The electron has a spin of plus minus h bar over 2, right? So it's plus minus h bar over 2. So there is this h bar over 2. Okay. Actually, you know what? Let me just derive this for you. That's easier. The electron magnetic moment is minus UBH S. Okay. Like I said, this is 2. This is a Bohr magneton, and it is something like 4.7 times 10 to the minus 9. Okay, you can look it up. And this is just the spin quantum number. Okay, S. So the projection of S, rather, is h bar m, and m takes the value of plus minus 2, plus minus half, 4 electrons, spin half, right? So we know that this is basically this GUM, and m, the magnitude. The magnitude is GUM, and m is 1/2. 1/2. Okay, let me just write 1/2. Okay, mu is the fundamental unit of magnetic moment, so it has half the fundamental unit of magnetic moment. That's what electron has, and this general magnetic ratio is about 2. So this makes this. Sorry. This makes this. Yeah. So overall, the electromagnetic moment is the fundamental Bohr magneton. All right. Now, the reason I want to mention this is because I want you to notice something that is very special for electrons, which is this minus sign. Okay. This minus sign makes the energy, makes the Hamiltonian cancel with this minus sign, the energy Hamiltonian. Therefore, what you have is this. Yeah. And if so therefore, your energy is U B M. I'm just gonna write it in the general form. B and M. Okay. So for plus 1/2, you have a positive shift. Okay, that's important. That's one going with this. For spin up or positive 1/2, you have a positive shift, and for minus, you have a downward shift, negative shift. Yep. So together, the overall shift is how much? Yes, G mu B. And of course, this B is the parallel component, right? Let's not forget that. Yeah. So this is the result. So this is the result for a single electron. The gap, the energy gap that is open by the magnetic field. This is for one electron. One electron. Okay. For 2 electrons, of course, they both spin up. They add. They both spin down. They also add. So for 2 spectrum, you have another factor of 2 here. That's for 2 electrons. Okay. So this is a physical picture of it because you have 2 electrons. And for this, you can imagine that for this, one goes up, one goes down, so there's no shift. Therefore, it doesn't matter for this. It does not affect this. It is still stay in its position. Yep. Okay. There's another way to look at this. You can say, oh, I have a composite system. I see MV as one entity, and it has the spin, a net spin from a 2 electron contribution. So S in this case does not have an n of plus minus 1/2, but have plus minus 1, right? And of course, in that case, the shift will not be 1/2. The shift will just be G mu B parallel up and minus G mu B parallel down. Yeah. And the total will be just 2 G mu B. Okay, you can see it that way too, as a composite spin object. Either way works. Yeah. But I kind of like this 2 electron 1 electron picture because that helps you to see how physically they add up. All right, so this is my number 1. Second, so now since we have this 3 distinct levels, we can choose to use like how many. Okay, now how many qubit pairs are here in this 3-level system? 3 pairs. A pair involves 2 states. Oh, yes, you're talking about this. Yes.
The down and middle.
Right. I got you. So, Mustafa, he's thinking about this. He's thinking about this, and this, and this. Right? Okay. Yeah, he's right. There are 3 pairs. Yes. But in order to utilize the qubit, the first thing we need to do is state initialization, right? And to do that, we use cooling. And for MV, we're only able to cool it down to the n equal to 0 state, right? So this will be our starting point for every operation. Therefore, yes, although physically there are 3 possible qubit pairs, only 2 are acceptable to us because we are always starting with n equal to 0. If there is a way, to cool the system to this state, okay, then that also gives you only 2 pairs. Yeah, if there's a way to cool the system to this state, that also only gives you 2 pairs. Okay, so mathematically, yes, 3 levels, but physically, only 2 are practically available to us. Okay, so I'm gonna choose this one and this one, 2 states. All right. Now there are 2 pairs available to us. We can use either, and I typically will prefer the lower one. Yeah, that's just my personal preference. So you can assume that this is always the case when I discuss this spin thing. Okay, maybe a little word about this. Are you all familiarized with this form? The minus mu dot B, the magnetic energy. You can see this if you don't remember if there's a minus sign or not. Okay, if you don't remember, you can see this from a magnet. Yeah, so for a magnet we have mu from south to north. Okay, and the magnetic line is from north to south. Okay, yeah. Now when we have so here at this position, it is opposite to its magnetic moment. So if I call this mu1, this is going to be B1. Okay, this is B1. Okay, now if I bring in a magnetic moment, if I bring in another magnet like this, right? From your experience with playing of playing with magnets, you know what's gonna happen, right? If you don't hold it, then somehow you will just get rotated and will flip. You'll get attracted and you'll flip to this direction. And that is because we know from the basic physics principle, you always go from a high energy orientation to a low energy orientation, right? So this must be a high energy orientation. This must be a low energy orientation. Okay. Now we know this is mu2. Okay. So here we have. Okay, it's easy to remember that this will be the interaction term in terms of energy. But do we have a minus sign or not? Well, and you can see here we have the opposite orientation, right? So this is a minus value. This gives a minus value for energy. And this, we have a parallel orientation. So this gives a positive value for energy. Not for energy, but for interaction. Okay, so this is minus, this is positive. Next, this is negative, this is positive. If negative should become the high energy state and positive should become the low energy state, then that means we need to put a minus sign here. Okay? So this is magnetic field interaction. On the other hand, for electric field interaction, we also have a dipole coupled with the field. But then here in this case, there's no minus sign. Okay, so this minus sign is special for magnetic interaction. Okay, and this we should use for a Rabi model. Okay. Now, so suppose we have a ground state, an excited state. Okay, and of course this is made of -1, this is made of, so physically this is made of -1 and 0. Okay, and we use this as our MV qubit. MV qubit is actually a special case in a broader category. There are a lot of things that have similar electronic structures as the MV center, although they operate at a much lower temperature. So for this type of qubit, we call it color center qubit. As a general name. Okay, you have nitrogen vacancy, but you could also have silicon vacancy. You can have a lot of other vacancies and different hosts, and they all together give different physical properties on its operation condition. Right? So say we have this qubit and we we have prepared it in the ground state. Now in your experiment, you offered a microwave pulse to drive it, right? Okay, so it goes up. Yes. Now, on your if we can monitor, and yes we can monitor with the optical fluorescence. If we can monitor the population in the excited state, what do we see? Of course, we see this, right? We see it reaches to a peak Give me a second. Okay. Now the question I want to ask is, if I continuously drive it, what will happen? I don't know what this value is, by the way. Okay, so on a scale from 0 to 1, I'm not sure if this is 1 or 0.7 or 0.5. I don't know. But so say I drive it and it kind of reaching the maximum. As you can imagine, right? If I drive it, it will go to the max. It will go up. So this we can expect. But what happened? Yes. But what happened if I continuously drive it? If I just keep my microwave drive on? What will happen?
It would saturate.
Yes, that is a reasonable. So it will saturate like that. It will just stay there. What? It will oscillate, but why? So someone say it will oscillate, some kind of oscillation, right? To oscillate, you must go down, right? So let me just take this first part. You have to go down, okay? So it's possible that you go down or you stay, but which one will happen? Logically, from this picture, I can only say that the only logical conclusion is that it will stay. Because once it's there, and if I drive it further, there's nothing in the ground state for me to drive up. That's a good point. Okay, so yes, I drive it there, but if I continuously drive it, yes, it won't do anything. However, somebody say that there's finite lifetime for the population to stay here, right? So eventually, it will go down. It should go down, and that's what you expect, right? And that might be true, but this happened at a very, very large, has a very, very large tail that happened at a much later time. The time scale, the relative time scale, okay? The relative time scale between this and this is about 100 nanosecond, about. This is about 1 millisecond. Okay, so compared to this time, this is like forever, right? So you have -3, and here you have -7. So there are 4 more orders of magnitude difference. 4 order of magnitude difference. So that's almost like what? A minute to a year? Yeah. So this is like forever. So for the foreseeable future, it should stay. It should stay there. We don't need to worry about the relaxation to the ground state. Okay, it should stay there. However, is this what you see in your experiment? You have not. Phoenix have not done the experiment. Tom has not done the experiment, but the 3 of them have. Is this what you see when you drive it on nonstop? Does it just stay there? It goes up and down, right?
Yeah.
So that's kind of puzzling. So instead of doing this logical thing, it chooses to go down at a fairly short time scale. So what's the physical cause of that? Okay, and as a matter of fact, it does not go down only. When it reaches to the bottom, it bounces back, right? It does this. It kind of oscillates. So what's the physical cause for this? Well, when we offer a microwave drive to this qubit, okay, there was not only one microwave photon, but billions and billions, right? So there are like so many of them. So many of them. How many of them does it take to make an excitation? One. Because if the photon energy is the same as the gap energy, not a gap, but as the energy gap, right? On resonance. If that is the case, then yes, it's only logical that it will only take one photon to absorb one photon to make this energy excitation.
Is it similar dimension?
Yes. But, so yeah, we're gonna go to there. But once it get up there, two things can happen. We all have heard of Einstein's, probably not all of us, but some of us have heard of Einstein's AB coefficient, right? How many of you have heard of Einstein's AB coefficient? 1, 2, no? How about you? Have you heard of it? Yeah. If you heard of it but not understand it, it's okay. I'm asking if have you heard of it? Einstein's AB coefficient. Okay. At that time, it was only the beginning of quantum mechanics. People are still trying to figure out what this thing is. And Max Planck just proposed his recent idea of photon condensations, and Einstein had the same idea. None of them have Schrödinger's equation. Schrödinger comes much later, right? Not much later, but later. Or Heisenberg's equation. Okay, those players come later. So at first, but they were already able to do some experiment, some spectroscopy experiment, and so they see that light can get absorbed into materials or atoms, and it also could, this atom or material can fluorescence, it can release energy. Okay, so they see all that. They don't quite understand what's going on. They don't have a physical model for it. All right. So Einstein at that time came along, and he has proposed array equation. Array equation is basically like moving marbles between two buckets. So he has proposed array equation, and that array equation involves two types of coefficient. Coefficient A represent incoherent interaction. That is in modern language, incoherent interaction. At that time, they don't have such term. Okay. B is coherent interaction. Okay. And coherent interaction, of course, will include absorption. Yeah. But once you are up there, two things can happen. You could have spontaneous emission, or you could have stimulated emission. At that time, that was just a hypothesis. Okay. But Einstein was spot on. Okay, that's the genius of him. He was spot on. There are two kind of process that can happen. One is spontaneous. Sorry. One is spontaneous emission. Okay, so that will bring the population from the excited state down to the ground state. And the other is, let me just write this, stimulated emission. Okay. Later, we learned that these two processes actually have the same origin. Okay, how is that possible? Yeah, it looked like two distinctly different processes. How is that possible? They have the same origin. Let me first say something about the spontaneous emission. Okay, so this is till later we understand this. At first they didn't know this. They only have this phenomenological equation, the AB coefficient rate equation. Okay, but this detailed macroscopic mechanism was understood at a later time. When we have that population up here, and we stop our drive, okay, we don't perturb it. In principle, nothing could happen, right? Because nobody is interacting with it. So it should just stay by itself, right? If I put you in a room and I take away your phone and it's only you, right? Will you suddenly start to laugh? Or will you suddenly start to cry? Unlikely. You're not going to do anything. You're just kind of going to stay there and being idled, right? So you're not going to do anything. So it is a puzzle at first why spontaneous emission could happen. This is actually a pretty profound question. Because we do observe it. It does not stay there forever. We do observe this. So what happened? Well, huh? Say again?
It prefers the minimal energy state, so specific time scale it will.
No. I'm sorry, no. Because only when there is an interaction, then you will have this motion moving from the high energy state to the low energy state. Only when there is interaction, like the case of our magnets, right? If you put a magnet there, it won't flip by itself. Yes? When you put a magnet that are very far away, even though they are in the same direction, if you put them like maybe 2 meters apart, it won't flip because the interaction is so weak, right? So in the absence of interaction, there's no such things as high energy state or low energy state. It's just nothing. This reference does not exist. You cannot compare the two orientation because they are identical by symmetry. Really, it is the introduction of interaction that breaks the symmetry, breaks the degeneracy of these two orientation, and making one the high energy state and the other the low energy state. And only when that happens, you can say, oh, the natural tendency, the physical principle is that it will always go from the high energy state to the low energy state, right? Okay. So, but in this case, like I said, I just put you in the room 620. After we all finish our lecture and we go to the lab, I just leave you here in the room and lock the door, right? Of course, after a while you will scream, but that's besides the issue. But in principle, we shouldn't really do anything because it's just all by itself. Okay, I want you to just take a moment to take this in. This is the only logical conclusion. It shouldn't move. Okay, it should stay there. So the fact that it does go down implies that there are some kind of interaction, even though there's nothing around it. Okay? So why is that? After the development of quantum electrodynamics, we understand that when there's nothing, there's really nothing. It's really not nothing. The electromagnetic field in the vacuum, so without any source, without any flying photons around. Yes. The ground state, the quantum ground state of electromagnetic field actually produce photons for a brief moment. Okay. These are called the vacuum fluctuation. Okay. Vacuum fluctuation. And this is key to many important phenomena, such as Casimir effect and length shift. Okay. Richard Feynman, who is a very well-known, renowned physicist, I'm sure many of you have heard of him. He had his Nobel Prize on his work on quantum electrodynamics. And a big part of it is to deal with interaction, electron interacting with vacuum fluctuation, or some people call it the virtual photons. The reason it's called virtual is not because it does not exist. It's because, so this is the picture I usually give. Imagine the electromagnetic field is like a sea, okay? A pond of water, sorry, a pond of water, okay? And once in a while, some water droplet forms and they pop out from the pump and they fall back after a brief moment. Okay, when that water pops out from the body of the water body and become like an isolated entity, that's called photon. Okay, the difference between real photon and virtual photon is that virtual photon fall back to the sea, but real photon does not. Okay, so there are two ways you can make photons. You can disturb the sea. One is that because it's quantum, so it will disturb itself. The fluctuation will disturb itself. So, here and there, waters or the droplets, and they fall back. The other way is you intervene actively, and you splush the water out. Okay, so you can get the water out from the sea and you produce real photon. And the photon will just exist for a long time, indefinitely, until it gets absorbed. But this will fall back to itself. So this is the difference between the real photon and the virtual photon. It's only in the time. Virtual photon. Okay. So this is long time. This is a short time. Okay. But when the moment when they are out from the pound of water, they will interact with matter just the same way. Okay? There's no difference. So only the difference is the time and how often this happens. Yeah? So the deal is this vacuum photon once in a while pop out from the vacuum. And it will pass by, okay? You fly by this MV. And because photons are bosons, they like to, if they see a partner passing by, they will just want to jump on the train. Okay, so that gives you that stimulated an emission. Okay, and I'm just going to use a stimulated emission. Okay, but this will be gone in a brief moment, less than a femtosecond, less than an attosecond. This will be gone very soon. But the photon that was stimulated emit will stay, and that's what you see as fluorescence. Okay, so you absorb this, but you do not absorb this. So it all appears like it just do this emission all by itself. That's the word spontaneous, because you absorbed one photon only. You do not see the other one that's stimulated. Okay. On the other hand, if we actively disturb the water and splash it and make a lot of water droplet come out, then you can imagine that there are like just tons of photons present. Like there's only one, but here we can have many, right? And any one of them, of course, can cause the same thing to happen. So let's just take, say, this one, okay? Well, actually, no, it's not an absorption, so it does not take one, everyone. So this is everyone. Also, by the virtue of stimulated emission, the energy is released radioactively, and it moves the population down to ground state. Okay? And here, because we see everything, we see both your input photon and this additional photon. We call this stimulated. But at its core, at its heart, both are stimulated emission. Yeah? So really, nothing is not nothing. The void, there's a lot of things in the void, as some people say. Okay, there's plenty in the void. So that's pretty cool in my opinion. All right, let's come back to this. By the way, just want to mention something. Vacuum fluctuation. So we have not covered this, but we will cover this in our lecture of field quantization. In its ground state, the electromagnetic field has 0 average value. Okay, so that's why you cannot absorb it, because a lot of times what you see is the result of interaction between the E field, and even if you use photodetector, it is still at the fundamental level. It is the interaction between the actual dipole moment and the field, right? So it is the field, and since the field is 0, a lot of times you just don't see it. Okay, but the field square is not 0. Okay, so how do I picture this? You can see this as a Gaussian. Okay, so E is here. It's 0 most of the time, but once in a while you have positive value or negative value. It does not oscillate like a sinusoidal wave, but it fluctuates between the two values. So in average it is 0, but it does have a width. Okay, an non-zero width. Okay, so this is vacuum fluctuation. All right, so let's come back to this. So this explains why this goes down, because of stimulated emission. Okay, and when we reach the bottom, of course, in this process, you have part of the population stay in the excited. So here I'm drawing for this 1 MV qubit, right? I'm sorry. This is still pertains to 1 MV qubit, but when you go down, it is, since this is a quantum system, superposition is allowed. It's possible. So it's not definite. It's not definite that it will definitely emit. It's just that, sorry, it is not definite that it will go down. It's just that the likelihood of finding it in the ground state upon detection increase with time. Okay, increase with time. So this is a probability. Okay, when it reaches here, that means if you make a detection here, there's 100% probability that is going to be found in the ground state. But for other times, it is in the superposition. Okay, so that's how you read this. Okay, and this represents 1 single qubit. All right, so you go down, and once you are all here, the same process goes again. They will count another photon and will absorb it, and then stimulate emitted emission, and so this just goes on forever in principle. All right, so Rabi
when you oscillate, the minimum of P
Yeah.
will go to 0.
Yeah.
Why? Why will not be a number larger than 0?
Why should it?
I don't know why you
Because this process just keep going.
Yeah, but in
0 means it's in the ground without it.
you're talking about, I think you're thinking about this. Wait, where's my black? You're thinking about this. But I'm saying why should, what's the reason for doing that?
I think not all 100%.
Why? I'm asking why. Is it logical to do that? Just like the discussion we had, right? When we reach to some kind of maximum, it's only logical at that moment of discussion. It's only logical for it to stay flat. This going down was an experimental observation. And that get us to rethink what we know. And at that time, we have not talked about stimulated emission yet. And then this prompts us to think about the emission process, and then we have this, right? Okay. So it was the experimental observation that prompted us to make an explanation for this. But at that point, the only logical thing is for it to continue in this position, given the physical element that we have talked about. Yeah. So given the physical element we've talked about here, I don't see why there is any reason for it to stop halfway and then get up.
How many electrons?
This is one. Just one.
So many electrons, like our experiment, the PE curve will not drop down to 0.
Well, still, everyone is identical. All of them are identical. They interact with the magnetic field, with the electromagnetic field, with the microwave in identical way. So what happened to one person will happen to the other person, just like the flu, right? When you caught a flu, you cough and you sneeze, and then you feel muscle ache. When he caught the flu, same thing will happen to him, right? Everybody will experience the same thing. Okay, so the probability interpretation for single particle is the same as the ensemble interpretation. See what I'm saying? So that's the basic. So this is I think this is called a Copenhagen interpretation. Okay, so this is the fundamental thing about to interpret the quantum mechanical probability. The quantum mechanical probability has a twofold meaning. It can apply to a single particle. Okay, when you apply to a single particle, that means you repeat the experiment many times. Every time you prepare in the same initial state, and you do it, and you do it, and you do it, and the experimental outcome will likely be different every time. But overall, if you take the statistic of all your experimental trials, okay, then you will find that maybe 3 out of 7 times it is in the ground state, okay, and 4 out of 7 times is in the excited state. Therefore, you record, I have a probability of going down to the ground state as 3/7, okay, and the probability of remaining in the excited state is 4/7, right? So this is the probabilistic probability interpretation for single particle. But for many particle, it's equivalent as repeating the experiment, because every particle are identical. So it's equivalent, physically equivalent to, and of course we ignore the inhomogeneity of the microwave field. All right, so we just pretend that it is homogeneous, and then it hits every particle in the same way. Okay, hits every MV center in the same way. So if we just like apply this field to a bunch of them, and they are all identical, then what you will find is 3 out of 7 particles will be in the ground state, and 4 out of 7 will stay in the excited state. So the ensemble statistic and your single particle probability are the same. And this is the basic quantum mechanical postulate.
My question is, if in any of these systems you draw this picture and you say at a certain time t, there will be all of them
in the ground state. Yes, and that's what I'm stating. All of them, correct. If you have 100% certainty for one to be in the ground state, then even you have a million of them will be in the ground state. That is my statement here, okay? Because there's no other reason for you to do otherwise. And of course, if you include more physical element into our discussion, sure, you probably will have different results. But pertaining to our discussion right now, all of them will be in the ground state. Okay?
One can go to ground state a bit earlier
No.
By the next photon?
No. All of them will achieve. If they are all initialized here, and I apply a pulse, a microwave drive starting from this time, then at this time, all of them, if I have a million MV center, then a million of them will be in this state, in the ground state. That's what I'm stating here. And that's the only logical conclusion we can make at this point. Mm-hmm.
You say green line will in short time window we may see the green line is a constant.
Mm-hmm.
And what kind of case will make the oscillation happen?
At the same short time, yes. So at the same time scale. If it takes 100 nanosecond to reach here, then to reach the maximum, it takes just double the time. And to reach the next maximum, it is just another 100 nanosecond.
Green line is the envelope.
No, green line is the long time, very, very long time decay. Okay, so this is the exaggeration. At this time scale, so here I have maybe a maximum, I have 700 nanosecond span, right? So 700 millisecond span is like here. All right, so for the green curve, it is like here. And of course, I cannot show you the tail if I draw it to scale.
So if I open my microwave for 1 millisecond, and I will see the green line.
Yes.
And I open, and if I just check for the first 200.
Well, okay, sorry. If you turn your microwave on for that long, okay, no, you will not see them all be in the ground state, because when they are in the ground state, they will immediately at the 100 nanosecond scale, immediately get excited. So this curve I'm driving, I'm plotting is perhaps it's only fair if we stop the microwave at this point and we just let it stay there, and we wait for one millisecond, and it will drop to the ground state. It will relax to ground state. Okay. So what happens if there are two processes competing? If there are absorption stimulated emission and spontaneous emission, like if they are all competing with each other, what happened? And of course, at the short time scale, this will dominate. The coherent interaction will dominate, so it will oscillate. Okay, at the long time scale, well, this will start to play a role too. But what will happen here, this is not discussed in the Rabi model. Okay, the Rabi model, that's a good point. The Rabi model only concerns with the coherent interaction, as I will explain that later. Okay. All right. So I guess this is now a good time to take a break. Okay. So let's take a 5-minute break and we'll reconvene here. Take some water, go to the restroom, take a leak.
Have you checked the system that we were doing? It was crashing all the time.
Say again.
Have you checked the system that we were running? It was crashing all the time there.
Yeah, I have not, but the TA told me that. Can you show me today?
Yeah.
Yeah. Show me today so I can. I'm okay. I have used it, and there was no problem when
the first time it's not wrong, but you're using it continuously.
Yeah.
Then it keeps crashing.
I think it's probably some kind of parameter issue. So you need to show me.
When I take like for 300 data, it's okay. Then I send the second program for 300 data, it crashes. And like
300 points.
Yeah.
Do you append it?
I mean, an example is like that.
So you
if I'm trying for a bigger one, it crashes at some point. So it's like.
So maybe up to like 3,000 data points, it crashes.
Yeah, that means, but it's like the longer you are running, it crashes more early and early.
Oh,
so
maybe there.
Like
and if you restart it, then the crash time. You reset the crash time.
Yeah, but you cannot do anything other than like if it's crashed, you have to close the application.
Right. And if you open it, then you kind of reset the process, and your crash time.
It's a bit early.
Is it earlier than before, or
Yes,
is it the same?
It's earlier than before.
Okay, so it gets shorter and shorter each time you.
Yeah, I think so, because like when I started the lab last time, we were like 1,500 data or something in a single run. It was all right. Then we were taking like for 3,000 and it crashed. So we closed it. Then we were doing 300 sets, and the first set we got, second set it crashed. Then the third set we got, fourth set it crashed. Then at the end, like even one set was like crashing.
I see.
And it happens like in the before labs also, but it was like those data sets were much shorter. So like whenever it crashed, we just close and open and it take the other data.
Okay. Yeah, that is okay. That is very likely an internal memory problem. And does the other group has the same problem?
No, really.
Not really.
But we check the memory also, means the RAM of the system. When we put like 6,000 data set, the memory get full and get another error. It's completely different. In this case, it's like only going to 7 GB where we have like 32 GB or something as the RAM. So
yes, but there are more going on with the RAM. There is also. So the RAM is the RAM of the computer, but there are other boxes in the computer that does the data acquisition. Okay, and those are black box to me. I don't know how they work. I don't know the specifics. I don't know the specs. I don't know how they designed. All I know is that this system that we bought is not very robust. So if we try to do a lot of work with it, like a heavy duty thing with it, for sure something will go wrong. Like for example, if I want to take a long time, for example, if I like in the pump duration scan, remember?
Yeah.
I told you guys to do 3,000 microsecond, right? If I go beyond 3,000 microsecond, like 4,000 or 300, 3,500, it will crash.
Yeah, I mean, like we check that. I mean, similar to that, like like when we are doing like this. So in the RAM case, the thing about the software is when you get the data set, it will take all the RAM it need at once, then fill it up. So even we are at the starting point, because the RAM short goes like, okay, this much RAM we need, we are good. So if you get more than the RAM it has, it will crash immediately. But if it's not like it takes that much, I mean, in case of RAM, that was happening. So
yeah, but for
that's
for
like
what I said,
4,500 data set, it takes more than RAM at the initially and crashes.
But what I saw was it kind of just go to a point and it does not continue anymore, even though even though it accept my my setting at first, and it start running, it will run to a point and it will just stop there.
I think in the second system, they did for 6,000 without crashing.
Okay.
So in our system, we couldn't even give the 6,000 command, but in the other 6,000, that didn't take that much time.
Yeah, and you know there's also other things involved.
Yeah.
Like when you are turning on and shutting off the microwave, there's a switch involved, right? And so there's like a sequencer, like a box. It's called sequencer, and I don't know how it works, and maybe there's some kind of limitation. Maybe like I don't know,
like
overheating.
The error we get is like something not detected. Some cable is not detected. Something error we get.
Some card is not present, like that. So like some kind of connection to the hardware is lost.
Yeah, exactly.
Yes.
And we try and refresh it, you don't get it, but if you close and open, it's out.
Right. Yeah. So this is, I would say this is a problem that cannot be fixed. This just has to do with the specs of the hardware. And so if you I'm sure if you just do manually 300 every time, if you don't do it at the beginning, if you don't do the wrong run at the beginning, if you don't do like the pending at the first, and you just do 300, I'm sure it will work fine.
Yeah, but even sometimes it's crash, you have to do it again at that stage.
Well, yeah, but it will be much less frequent.
So in the earlier labs, we had the crash, but we were
I understand. You all of a sudden you just go. I had that experience too, and it's kind of just random, and I blame that to the instability of their hardware. I think it's really a hardware issue.
Some cable issue. I mean, some cable is not properly.
Sorry, somewhat.
Some cable.
Cable?
Yeah.
No.
Means like the error was something like some cable not found or something.
Cable are only meant to pass signal between devices.
There is some
if you cannot detect a device,
software problem.
No, the hardware. See the box. Those cards are connect internally with the computer. There's like a slot. Okay, so that connection cannot be bad. When the computer cannot detect this, means it's shutting off for some reason. Maybe like a self-protection mechanism, or I don't know. It is proprietary product, I cannot ask them for their product number and look it up. I did not build this. Yeah. So I'm just saying that it is just what it is. And in order to do an experimental run without interruption, without like, having done this for 20 minutes and then all of a sudden crash and 20 minutes of worth of data are gone.
Yeah.
I would suggest that you just do this manually. Just one piece at a time. That's how I do it. When I do a 2D scan, I literally change the parameter once and I do a round. I change the parameter and do a round, and I just save like 20 files. That's how I do it. And I mean, that's the more robust way of operation, since their machine is not as robust. You need, if their machine is very, I mean, if you have a car, right, and the car is kind of flimsy, and you drive it with slowly, and you don't push the gas strong, and you don't brake suddenly, right? But if you're driving a Lamborghini, oh yeah, of course, however you want to drive it, you turn, you can do whatever you want to do. So as far as I understand it, it is really a hardware issue, since it's so random. If it always happens at the same, like for example, if you enter the scanning step or your pulse length 123 nanosecond, if you enter that number, then for sure it will crash every time, because the system does not accept anything but the integer of 10 nanosecond. So that's a software problem. It's programmed this way. So if this keep occurring at exactly the same condition, then yes, it's a software problem. But if it just happen randomly and it kind of shift, digress.
It is not because like when it crash, when that same data we run again, sometimes it doesn't crash.
Yeah.
You get that.
So from my experience as an experimentalist, I know that has to do with the hardware, and just something happened in the hardware that we don't know. So the only way to overcome this is just to operate with gentle and careful touch. That's the only advice I can give you. Yeah. EDU1, the machine that you operate, for as long as I have, like, as far as my experience concerned, it has been more stable than the other one. So I'm surprised to hear you say that.
Because we had this issue from the beginning.
Like the other one,
like Eddie and we were doing,
yeah.
We had the same issue. It crashed.
Okay. But anyway, that's all the information I can provide you. Right? Okay, we are gonna start. Okay, what was the number I have here? 3. Okay. 3. Thanks. So now I should have 4. Next time, before we take the break, I need to write this down. All right. Here I want to give you something that will be very useful for the rest of your life if you work on quantum mechanics, Rabi model solution. Okay? Believe it or not, this is very hard to find. The complete Rabi model solution is very, very hard to find in the textbook. Actually, I cannot find it. Well, I did in Scotty's book, but anyway, my point is, it is very hard to find, and if you find it, it's mostly confusing, because if you check different books, they are different. They're different. So what I give you here is test it, and I'm 100% sure that it is correct. So I'm going to give you this, something you can take away for the and benefit from it for the rest of your life if you use quantum mechanics again. Okay. All right. So this thing that we have talked about, is I'm going to take this a while. Take this out. This is just the phenomenology. Okay. Here is the quantum mechanical analysis of this oscillation that you observe. And this is called Rabi. This is built by Rabi. And Rabi is the last name. Okay. So this is developed by Rabi, and yeah. I'm going to just, so in theory, so the quantum mechanical theory is we have the Schrodinger equation. So this is the Schrodinger equation, right? Yes? All right. So because this has two states, AG and A being the amplitude. Sorry? Oh, this is the microwave amplitude. The microwave envelope. Okay. But it has oscillation inside. Okay, maybe I will draw it. Okay. Yeah. We usually draw the envelope only, but why not? So this is omega naught. Oh, sorry, not omega naught. Omega. All right. So the quantum mechanical probability, probability amplitude. I'm sorry, for the lack of sleep, not writing this right. Okay. So these are the quantum mechanical probability and amplitude, and we usually like to write it in another form. Okay. These are the physical interpretation of our notation, the ground state, excited state. The energy difference is h bar omega naught. Usually we omit the h bar, we just write omega naught. Okay. And since only the difference in energy matters, we will just call this zero. And this h bar omega naught. Okay. So Eg is 0. We define this as 0, and E is h bar omega naught. Okay. So those in the free, without any external perturbation, if you have a superposition, or if you just simply have some population in the excited state, its phase will oscillate at this rate. Okay. All right. So if we write this in this notation, then we can write this in matrix form. Hold on. Let me think. Okay. EG. G. Sorry.
The last term of the wave equation.
Here?
Yes. I don't know why the concept is
All right. So this means if you have a population, if you have some population in the excited state, right? Then it will oscillate. The phase will oscillate in its natural frequency. So say you have, if you have this, okay, if I just give you a general, EG is h bar omega g, and E is h bar omega E, okay? Then you solve we call this unperturbed Hamiltonian. Okay? The unperturbed Hamiltonian is simple. It is basically just EG EG with, yeah, it is actually just EG. In metric form, it is just AGAE EGEE. Okay, you see? And the solution here is okay, got it? So you see it will oscillate, the phase will oscillate at its energy. Yeah, and because we can define our energy, we can shift the offset of our energy. So we usually just make WG 0 and WE omega naught. So that's where this comes from. We factor out this natural oscillation. Okay, this natural phase oscillation term, and we focus on amplitude.
In this Hamiltonian you wrote, there is always like the amplitude. It doesn't stay in the same state. It always flips, right? If
Yeah,
you write Hamiltonian.
Yes,
like
I'm gonna explain this. Okay. All right. So you see this Hamiltonian has omega naught, and it has these diagonal terms. This is not a calculus-based course. I'm here to give you the logical connection between ideas. So I'm not going to spend time in teaching you how to do the calculation. Right? You just need to know how things connect. If you want to learn how to do the calculation, there's a lot of work you need to do. And it will first start with reading the book on quantum mechanics or quantum optics. Okay? So here, just try to follow the logic. And let's not get into technical details, otherwise we won't have time for the experiment. Okay? So I'm just saying, so here I'm just saying that typically you have these diagonal terms, and this diagonal term give you this phase oscillation, right? If we take this phase oscillation out and we just focus on this amplitude, then the equation, the Schrödinger equation, will come without the diagonal terms, and only the off-diagonal terms are left. Don't ask me why. Okay? And in this case, oh, by the way, here let me define my E field. My E field is this. With the initial phase. Okay, this minus sign is very important. This is my convention. In this solution I'm gonna give you goes with this convention. If you have this defined as sine omega t plus phi, then the solution will look completely different. Okay, you need to conform it to this kind of form in order for the formula I gave to work. Yeah. So this is very formula sensitive. Okay. So for before the microwave turns on, the probability amplitude does not change. They are all the same up to this point. Okay? And when it turns on, yes, they will change. But then after it shuts off, they're all the same as this point. Okay? So the solution I'm gonna give you is when this when during the time when the microwave is on, when interaction is happening. For this time interval, the probability amplitude goes like this. Okay. So this is a complete solution. Now there are a few notations that I need to define. For example, what is this? Okay, this capital omega. This capital omega is called the generalized Rabi frequency. The generalized Rabi frequency. This is what a lot of books call. And the generalized Rabi frequency is a sum of two square terms. This thing is called the Rabi frequency. Okay, so the modulus of chi is called the Rabi frequency. So the Rabi frequency is the generalized Rabi frequency when there's zero detuning, or in other words, unresonance. Rabi frequency is the unresonance generalized Rabi frequency. Okay, so when you are on resonance, that's the value. And Rabi frequency is basically the interaction between the dipole, electric dipole, EX, and EG means the dipole operator, the X operator. So here, EG, this is, it's basically a coupling term, a coupling between G and E. Okay. So this is a complex number and also a vector because it has three components, X, Y, Z. Okay. And this is the polarization of the field and amplitude of the field. Okay. And this detuning in my convention is defined as omega minus omega naught. That's the frequency difference between your drive and your natural frequency. Okay. In our book, it's the opposite. It's omega naught minus omega. But in my derivation, I think this is a more natural choice. Omega minus omega naught. Okay. So these are the definition of the notation here. Okay. And this interaction term is basically this Rabi frequency, the coupling plus the time dependence. That's the time. Huh?
X.
That's X is just X, the position operator. Yeah. So Ex is the dipole moment, electric dipole moment. Yeah. All right. But all of this are represented by this term. Okay. So for our application, right? Remember I told you. So here what we have is we have this interaction as d dot e, right? And d dot e is Ex dot e, okay? X being the position operator. And if you take the matrix form, meaning that if you put the Bragg and Ket, you sandwich it with the Bragg and Ket notation with this initial and final state, then you get a matrix element. You get a matrix element, and you also get a matrix element for the for the position operator. Okay, so that's how the notation works. Now, an important thing is for us, for the NV center, we know the interaction term is a magnetic field. It's a magnetic interaction, right? It is not an electric interaction. It's not D dot E, right? It is mu dot B, correct? And what's more is that there's a minus sign. Okay, so how can this? So for our application, we have let me write here. We have a minus sign. We have this, right? So this obviously have a different form than that. Especially there's a minus sign. So what do we do with it? Well, lucky for us, for electron, if you're talking about protons and like other things, neutrons, that's like another business. But for electrons, this minus sign is cancelled because the magnetic moment of electron also have an extra minus sign, right? So together there is no minus sign left, as we have discussed earlier. And B here is the magnetic component of the microwave or of the electromagnetic field. So B is so if this is cosine, then B is sine. Yes. Okay. So that's the difference that we have here. But basically everything can be reduced into the same form. Basically the same form as this, just with a different initial phase and a different Rabi frequency. Okay. But formally they are the same. Okay. So you need to be careful how to map this parameter into this. Okay. All right. Yeah. So EG. This is EG. EG. Okay. All right. So let's just do a little observation here. This looks like a very lengthy and random combinations of symbols, but actually it has very interesting structures. Okay, it has actually very interesting structure. And later when we learn about block vectors and block spheres and all this quantum information operators, gates and stuff, we will see that why there's a rich structure in here. Okay, but for now, I just want to point out that there's basically some kind of symmetry here. You see, CG has this cosine minus sine form, and CE has cosine plus sine form, right? There's some kind of symmetry here, and here you have this. This is kind of conjugated with that, but not the overall sign, right? But this is sine, this is sine. Okay. So at this stage, you can already see that there are some kind of structure built in. What's more is, if we imagine that we have an excited state to start with, we have a full population in the excited state, and we are driving it. We're driving it. What will happen is the ground state population will increase, and the excited state will decrease, right? So that gives us these two terms. Sorry, that gives us these two terms. This is excited state contribution to the ground state. So this is absorption. Yeah? And the corresponding term here, and the corresponding term is here, right? If you absorb, then the other one increase. But if we have a ground state to start with, and we drive it with a microwave, then we have, I'm sorry. I was confused. Sorry, I meant this. Sorry. First scenario is we have ground state and we drive it to the excited state. So this is absorption. Okay, and this is the corresponding term, the increase in the decrease. This is the increase of excited state, and this is a decrease in the ground state. Okay. In the second scenario is we have the full population in the excited state, and we drive it, and what will happen is we'll have stimulate emission. And in that case, we will have an increase in the ground state population. So that's this. This is emission. Okay. This sign, for the moment, you don't need to worry about this Rabi frequency term. But I want you to notice this. This plus and minus difference in the phase. See, this phase comes from where? This phase comes from the electromagnetic field. Okay. So you see, in the emission process, the phase contribute to the solution with a minus sign, and in absorption, it contribute with a plus sign. Okay. So that's one interesting observation. And the physical reason behind that is because if later, so the whole thing that we write here, this is called a semi-classical solution. Later, if we now we won't learn it, but we will learn how to do field quantization, but we will not do the full quantum version of the Rabi model, which is called the James-Common model. It has another name. Okay, but there you have two quantum objects, the quantum field, the quantized field, and the quantized matter interacting with each other. Here we have the semi-classical wave. We have the classical wave interacting with our quantum system. So that's why it's called semi-classical, because the wave, the drive part is treated as a classical entity. But if we later quantize that, you will see the raising operator, raising and lowering operator for photons, and those operators carry phase. Okay, and that phase is this. Okay, so already here you can see a little bit of the quantum nature of the interaction. Okay, so emission. So this process of emission, this will add a photon to the field. Okay, because when the energy was stored here, there's no photon in the vicinity, right? But once it decayed, it released photon, or it is like stimulated emission, it released photon. So the photon is added to the field. Therefore, we use a raising operator. Okay, and the phase associated with the raising operator is this. According to this notation. Okay, so you can see why this is a minus phi. And for this, you have the opposite. You have a photon being absorbed into the matter system. And in this case, we have a lowering operator for the photon number. And the lowering operator, you can see this is a conjugated operator, so also the phase is conjugated. Besides that, everything is the same. Okay, so you see why the phase here is positive and the phase there is minus. Okay, so you can say that the photon imprint of its phase into the matter system. Okay, and here imprint is not a proper word, but the same thing happens here too. Okay, so whatever the photon phase is, the matter has the same phase, right? This phase is critical later when we talk about excitation with more than one pulse, 2 pulse or 3 pulse. This phase will become very important. So in a later lecture called Ramsey interferometry, this phase is crucial. Having the sign right is important. Okay. All right.
Because you write from the ground state, so it cannot be from ground state. So it should be.
He's talking about the photon, not the atom.
Here this term is associated with the ground state, in the initial ground state. So assuming initially you are in the ground state, you have this term, you don't have this term.
I think she's talking about N dagger. That's of the photon, right? Not of the.
Huh? No, yeah, this is for the photon field.
One photon is reduced and one photon is added.
One photon is annihilated, taken out, eliminated from the field. You apply this operator to the electromagnetic field state, not the NV state. Yeah, this raising and lowering operator, they operate on the photon state. which we have not talked about yet. Later, when I talk about when I give a lecture on field quantization, we will talk about this. Yeah. Okay. Typically, if you want to use the raising and lowering operator language for a two-level system, you use this Pauli notation. Okay, and I think this is something like that, and this is something like this. Okay, so this is the raising and lowering operator for the two-level state. Okay, but for A are specifically reserved for photon fields. Yep. Okay, thanks for your question. All right. So that's, now I want to spend some time to discuss the application of this formula, like what does it tell us. And I want to focus on the case when we start with the ground state, which is most relevant to us. If we start with the ground state, okay. If I start with the ground state, my population, I will not. So in my solution, I will not have these two terms, right? Because these two terms are associated with the initial value of the excited state. So if we start with the ground state, then this will be 0. And I have these two terms. Okay. This is for the excited state, and this is for ground state. Yep. So I have two population. The modulus of this is kind of obvious, right? So it is simply just this. Pretty simple, right? The modulus of this is a bit difficult to calculate, okay? But you can use a trick because you know that the population must add to 1. The probability must add to 1, right? So if you know 1, you know automatically the other one must be this. Yep. Of course, you can also do a modulus of this and check the math, and you'll find this form. Okay. All right. So I want to focus on the behavior of this, and I see that we don't have time left. But this is, we're gonna keep going, but I'm gonna do it fast because this is important. And I'm gonna finish this part, and we'll probably cover the coherence in the later lecture. Okay. So first of all, you can see that this. So let's focus on PE, because PE has a very simple form, right? PE. P. You can see that P is oscillating in the period. What's the frequency of this? omega over 2?
It's a square of the time.
Yes.
Yeah.
So
It's
what's the,
half, I guess.
huh?
As we divide it by
No, you multiply by 2.
yes.
You double.
Yeah.
Yeah, why? Because typically
Yeah,
it's like
that's
this,
what I was
right?
saying.
And if you do the square, it's this. So instead of one period is like this, now the period is half.
Yeah.
So your frequency is doubled. Okay. So if you double the frequency, then frequency is omega. And this period is 2 pi over omega. Okay. So that's the first thing we want to note here. Okay. Now, and of course, this is, let's see. This is pi over omega, right? Yeah. So this is half of the period. This is another half of the period. So from 0 to 0. Correct? Okay. Now, I want to ask you, so this represents the drive. So this is proportional to my field strength. In that case, it's the E field, but for our case, it is the B field. Okay, the B field drive. Okay, so if I crank up my microwave intensity, then this becomes stronger. How would the oscillation period change? Well, it will become shorter. Yes, it will become shorter. So we know that. But what's the physical? So besides the math, besides the formula, what's the physical mechanism? So if you don't have this formula, okay, and you are doing an experiment, and then you just try to crank up your microwave amplitude, and you see that oscillation becomes faster. Could you think of a reason why?
I mean, more energy into the system.
Yes, but you're dealing with a two-level system, and then it can only absorb 1 photon only. So yes, having more energy, of course, I understand you're not talking about photon energy, you're talking about the bin energy, yeah, right? So the total energy. So what you're really talking about is the flux, the photon flux. When you crank up the amplitude, you increase the photon flux. Having more photon will increase the chance of absorption. Having a few photon around it, maybe it hits the MV, or maybe it does not, because photon also have a wave function. It could be here and there superposition, right? So having a large flux means that you have more realization of photon at different locations, and there's more chance for this to get hit, and so therefore it's more efficient. The energy can be driven into the system more efficiently. Okay, it can get pumped more efficiently. So for the same time period, the chance of the system absorbing energy goes up because the photon flux increase. Yeah, so that's a physical interpretation of this term. Yeah, so if this is lower, of course it goes down. Yeah, Okay.
Why PE drop quickly?
Sorry?
Why PE drop quickly? Decrease quickly? It is
Oh, that's a good question. So why does the PE drop also quickly? Why?
Simulated emission. So
The
like
chance
more-
of simulated emission also increase as you have more photon around it, right? So if you have energy in your excited state, and maybe once in a while a photon fly by, the chance of you seeing a decrease at a fixed amount of time, okay, can be increased if you have more photon that flies by. Okay, you see what I'm saying?
what's the relation between many photons fly away and our electron will spontaneous.
This is not spontaneous emission. This is stimulated emission. We have spent the first part of the lecture talking about this short time drop is due to stimulated emission. The long time drop is due to spontaneous emission. Okay? So the stimulated emission and absorption are both coherent interaction with the field. So with the photon flux being increased, the coherent interaction, the chance for coherent interaction is increased. Okay, so there's more likely for you to get up to a higher energy state in the same amount of time, or if you start from here, also from a fixing period. Okay, so for like this fixed amount of time, you see this can drop by this about this, maybe 20%, but here you can drop by almost 70%. Okay, and that's just due to the flux. More flux means more chance to absorb. More flux means more chance to be stimulated. Imagine there is a group of high school students coming to visit the campus. There are like 100 of them. Okay, the chance of you maybe try to do your homework at one of the cafeterias outside, outdoor cafeteria, and then they come by and they make a lot of noise and disturb you. The chance of you being disturbed is increased if there are two school bus of students coming to visit. But if there is maybe like a small team, like 5 of them, they could be anywhere in the campus. There's a little chance they will come by and disturb you. Okay, so that's the same reason. Okay, so that's the meaning of this. Both for absorption and stimulated emission, the chance is increased. Okay, now how about detuning? How would the detuning do to our curve, to this curve? Same? Let's see. According to the formula, right? Having a detuning, which means off-resonant excitation, should increase your Rabi frequency. So for a short time, you should go up in energy. That seems to be the implication. Yes? But that's kind of strange, don't you think? If you use a frequency that is just right to drive, this, wouldn't that be most efficient? Then a detuned, if this frequency is detuned, so that means it's not the same as this. Wouldn't this be less efficient? I would expect this to be more efficient than that, right? So what's going on here? This dependence of detuning in the Rabi frequency seems to violate our idea of driving on resonance being more efficient, being the more efficient option. Okay. Well,
According to the formula, I think like going up should increase, and but going down there is other term including the minus sign.
well, since we are running out of time, so I'm not gonna spend too much time in our discussion. But I want to point out to you this term. There's also this term here. Okay. This term is the maximum amplitude you can achieve. And if we expand it, you see that this is really just this. Okay? So the detuning not only affect the Rabi period, but it also affect the maximum probability you can achieve for reaching to the excited state. Yeah. So in other words, having the detuning will make my maximum drop. Yeah. So in that case, what really happened is instead of going up, I go down as I would expect, and then I reach to a lower value, but I oscillate faster. Okay. Okay. So this lower value, this lower maximum, of course, we understand this is just off resonant driving, right? We can even understand this from the perspective of classical oscillator. If we think of the probability of being in the excited state, if we just translate this as to the energy of the system, right? Because the energy of the system is the population in the excited state times the energy of the excited state, right? So if we just say this is, if we just conform this to our energy of this in the system, you can easily understand that, oh, sure, with the classical oscillator, if I do if I drive it in off resonant frequency, then I cannot pump energy into the system as much as if I would do it with the unresonant drive. So the energy pumping into the system becomes less efficient, right? So that's what this is about. This is about the energy. It is harder to pump energy into the system because you're off resonant. This agree with even our classical understanding of an oscillate of energy of a driving system, right? But what about this period being shorter? Okay, why is the period being shorter?
Because that's in the sign.
Huh?
The sign theta omega increases, that period becomes.
Sure, but here we, of course, according to the formula, it is this. But how do you know you have done the formula? If I didn't give you this formula and you're deriving this yourself, right? You need to have some kind of reference to check against your derivation. Otherwise, you might believe this is right, but it is wrong. So you always, when you, like, this is not, because we're not doing math. Math is a tool for us to make logical connection between ideas. So you will always have to return to the physics idea and make interpretation of our results, okay? So having to make the connection between the physics idea and the formula is an important it's an important step, and that's our responsibility as the reader to do. Okay, so I encourage you that whatever physics that you study, and when you are handed a formula, you always have to apply it to different cases and then just to think like, what's the physical cost for this and that? Okay. So the physical. So I just said this being in the denominator of the amplitude. This is because energy cannot be pumped into a system efficiently when you are off resonant. But here, there's another story for the deuterium to be in the oscillation period. This is energy oscillation period, right? So why it is there? We can, and after this I'm done. We can think of this as five, 6. Are you sure? 6. Okay. We can think of this as a swing. Okay? A swing. Swing is like this. Okay, this is my baby girl. She's about 1. So I put her on a swing. And if I place her here and release, okay, so actually she would do this. Her hair is like this. So this is the girl. Okay? So if I put her here, this is the starting position, right? And I release it, it will oscillate like this. Yeah? But due to the friction, it will slowly die out. So if I want to sustain the oscillation, I need to push it. Yeah? I need to push it. So say I have a little string attached to my hand. So this is my hand. Okay? Oh no, not a string, a stick. Okay? So I can push it, I can pull it, I can push it, I can pull it. If I do this at the same period as her oscillation, then I can reinforce the oscillation. I can put energy into the oscillation because I'm always pushing. I'm also always pushing her at the right time, right? But now, if I use a round frequency, which means I do this a little faster, or I do this a little slower. Let me say that I do this a little faster. Okay? I do this a little faster. Initially, I'm putting along with this. So the work is F times the displacement, right? So I'm parallel to her displacement. I'm doing the positive work. But then, after some time, because I'm doing this much faster, and she is still moving forward, but at this time, I'm already pulling back. So see, here I'm doing positive work, but here I'm doing negative work. Okay? So this kind of things happen. You see, here's another incidence. She's coming back, but instead of pulling, I pushed. So this is a good So here I'm pushing. Here I'm push against. You see? If I have a different frequency than her natural frequency, then for a brief moment I'll be pushing, but for a later time I'll be pushing against. And for a fixed amount of time, how much incidence you are pushing against? You're pushing against her oscillation, not determined how much negative work you do. Okay, so instead of putting energy into the system, you're slowing down the motion. Or if she is not moving at first, then you are kind of dissipating the energy that you put in at first. Okay, so the overall result is that she cannot swim very high because you're putting energy in, but you're also taking energy out. Okay, that's why we got. That's why her motion. Okay, sorry. That's why her motion cannot continue to go up, 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 up. At some point, it kind of slipped. Okay, the energy in the system cannot continue to go up. Because the work kind of slipped, and it's not driving it, and it's pushing against it. So it kind of just stopped. Okay, and go down. So it reached saturation at the earlier time. It will reach saturation at the earlier time. And that's what gives us a shorter period, because the slipped. Okay, the slipped push. Okay, so that's about it. Due to the time, we don't have time to discuss the spectral feature, the transient broadening and the power broadening from the Rabi model, also from the solution. I will see if I can try to cover it next time. And also the coherence in my next quantum spin lecture. Okay. All right. So we're not too bad. We're not doing too bad, but we are over time already. So let's try to avoid that. Quiz time. If I would have finished this later part of the lecture, this quiz would be very easy. It will be like a no-brainer for you guys, but I have not managed to do that. So this could be a little hard for you. Okay, so I guess you will just try. This is the time that we test whether peer instruction work or not. Okay. See if you can, through debate, get the right answer out. Lecture 1. Sorry, quiz. Quiz question: is Rabi oscillation a result of quantum interference? Second, is the resonance width in the Rabi spectrum equal to the spin's natural line width, or the okay. So for the first question, yes or no? Okay, come on. Let's not waste time. Line up, please. Is Rabi oscillation a result of quantum inference?
First one, first question.
Yes. First question. Yes or no? Very interesting. I'm very curious why you all choose yes and one person choose no. All right, so we're gonna have people debate with each other. Okay, Tom and Simon, you'll be one group, and the other three will be one group. Vida and Mustafa and Phoenix.
Can we look at the notes from the board earlier? Like looking for them?
Sure. Yeah, it doesn't matter. It's not there.
Okay.
I think it's better you spend your time on discussion than checking the board. It won't help you.
Yeah, the oscillations they are caused by the spatial
But you see, because we have emission and absorption, no, because we have both emission and absorption, we have interference.
I want to clarify a term because I heard over your conversation. Interference is interference. Something needs to interfere with another thing. It's not interaction. Interference and interaction are two things. Okay? And you have optical interference and you also have quantum interference. So that's completely different things. Okay? So don't confuse it with interaction.
Yeah. Contributed and oscillation is not quantum interference. What do you see in quantum interference?
I don't know how it's quantum interference, but I know that with interference, if they have some interference, we must contribute or non-contribute.
I mean, like when we have waves that interact, they distract or amplify each other. Find that. Quantum interference. We had
1 minute.
Yeah, but because it's quantum, it's not the classical interference.
There's no interference. Oh, except for optical. Yes,
Yeah.
optical is the classical interference.
Yeah.
Yeah.
Classical interference, optical interference. So I guess, like, for example, quantum interference could be you have two, you measure one of them, and it affects the other one, right? Could we say that we have it here? Yes, if they're oscillating together, I would guess. I'm not sure. We didn't come to coherence.
All right, thumbs up. Okay, get back to your line, please. Oh, now, do you want to change side? If you want to change side, do it now, please. Do you want to change side or not? Okay, have you made up your mind? And change side. All right, let's do a second round of discussion. Okay, this time Vida and Simon will be one group, and you three will be a second group. Oh, actually, I'm gonna make you and Vida and Simon in one group, and you two, Tom and Phoenix, will be discussing. Okay.
Okay, yeah. What do you group say? What do you think?
We talked about the Rabi oscillation that happened due to the spontaneous and stimulated emission and absorption.
Yes.
And we said that that's in multiple. And it depends on. I'm not sure about interaction versus interference.
Yeah.
In a certain direction where the photons interact.
I guess you have quantum interference if you have two photons, and if you measure one of them, it affects the other one. So I guess that's
yeah, I don't know what interference is defined as. You know.
That's oscillation. That's what I'm
Yeah, but I was thinking because we had like energy levels.
One more minute. You should try to convince each other that you're right, and you need to believe that you're right. You're not trying. This is not about deciding what's the best answer as a group. No, this is about like individual defending his answer and trying to convince other people you're wrong. Even if you're on the same side, but you probably choose this side for a different reason. So you need to attack the other person's reason, logically, of course, not physically, and then challenge it, right? So that's otherwise this is just a waste of time. Yeah, we're investing time in doing this. We're taking time from your experiment to do this. So let's make this work. So
often you get stuck on the definitions in the
it's a
questions. So when you like, yeah.
I can't argue for or against, I'm just guessing.
Yeah.
Well, interference you can see from the optics experiment.
Yeah,
you have one beam interfering with the other beam, and then there's some feature coming out, right? Yeah. So interference typically involve at least two objects, and when they are together, a new feature will come up.
In this quantum interference is between two photons, right?
No.
We are talking about
no.
electrons.
No,
right?
we're not talking about photons. We don't have photons here. Here we have a classical wave, magnetic wave. Sorry, electromagnetic wave, and we have a quantum two-level system. So the only thing quantum is that two-level system. So if this is quantum interference, that must be pertaining to this two-level system.
Yeah.
Okay. So that's all I can tell you.
Yeah.
So focus on the two-level system.
I think then it's yes. the radio oscillation is not because of the photon, it's because of the true deficit. Also because of the frequency of photon is out. But
What are you doing? You're just trying to hear their discussion. You need to believe in your intuition, right? Like you choose no, right? And you choose yes.
I choose yes, but
No, you need to believe that you are right and she's wrong. For some reason, she doesn't know, and you need to save her. And you need to do the same for her, for him too.
I asked her question about
He's very confused. You need to save him. You need to help him to get this bonus point. You're a very kind person, and you're here to help him. Okay? So believe in yourself and try to convince the other person.
So to say to be interference.
Because we're only looking at one electron, right?
There is a lot of electrons inside of the two-level system, right?
Yeah. But are they interacting? Or
All right.
Yeah, that's the thing.
I'll give you 30 seconds more. 30 seconds.
I think we must be interacting in some way, otherwise we cannot stay in sync before the detuning.
Okay, and that's interaction.
Yeah,
And that should be on the no side.
and then it's more interaction, yeah.
Well, what is the difference between interference and interacting?
Interacting, it's just affecting each other. But interfering if it's like the probabilities and the waves.
Believe in your answer. Convince other people. If you have nothing to do, go convince them. Okay? No. You need to assume that you are right and you convinced other people. That's how this works. And in a very heated debate, you are.
if we take this as like that, not this as that, then we don't need this.
Yeah. When you are off diagonal, which would suggest
All right.
interference, I would
Thumbs
say.
up. Thumbs up. Go back to your position. Go back to your position. Go back to your line. If you want to switch, do it now or never. If you want to switch, do it now or never. Who else want to switch? No one? All right. Yes? No? No? Yes? Okay. Answer is yes. It's quantum interference. Okay?
Is it because of the off-diagonal terms?
No. Had nothing to do with that. That's in the second part, the third part of the lecture. I feel the cover. Okay, so next question. Is the resonance width in the Rabi spectrum equal to the spin's natural line width? Okay, I don't know if these words all make sense to you, but just try your best to make a guess, okay? Okay. So that means this. So this is what we usually call a spin, quantum spin, okay? And this is the ground state, and this is the excited state, right? So when you're here, you decay, right? And that decay, the effect of the decay, usually put a frequency uncertainty on the excited state.
Okay.
Okay, that's called the natural line width. Ask Phoenix, she knows what I'm talking about. Okay, so this is spin natural line width. Basically, it's the line width of the excited state. Okay,
And the resonance width.
and the Rabi spectrum is when so this is omega 0, right? And when you, for like a fixed period of time, when you drive this, of course, at resonance, if you reach the maximum, then with the tuning at other frequencies, of course you will go lower, right? So as you scan through the frequency of your microwave, you will see like a population having like this shape, and this is the width. This is the width, spectral width. Okay. So here you have a width. Here you have a width. Here this is more like an excitation width, and here is like yes, a spectral width. Anyway, so that's so much I can tell you. Okay, so just try your best to make a guess. Yes or no? Okay, even though you didn't get the first question right, you can still play the devil and try to screw other people up. Okay, try to confuse them and challenge them, and then make them choose the wrong answer, so they don't get the bonus point. All right, that's getting 2 lines. Okay, that's not waste time. So already past 5. Yes or no? Is the natural resonance width in the Rabi spectrum equal to the spin's natural line width? Okay. So we have you in the no line.
I haven't had time to decide, but I can think later.
Okay. All right. So these are our initial distribution. Fine. Okay. Now that's we'll have Simon discuss with Phoenix, and the other 3 will be in one group. Well, by the way, Phoenix is an expert in spectroscopy, so she knows exactly what I'm talking about.
I'm not sure. Spin's natural line width, it's like how much. That's my question. If we do. And I guess since the I don't really know, but I guess maybe since you're adding, you have the photon absorption first, so like the excitation. We excite it from the ground level up, right? And when it by stimulated emission, it goes down again. The question is when yeah,
It's not equal to that. It has like other contribution from the microwave we are putting.
What was the question?
I think that the speech measurement also is a part of this radio selection, but it's not the only part. There is like part of the microwave that we are also putting to produce it. So I think it's not equal to that.
yeah, it's correct.
It has some other component of the microwave. That's my question.
Okay, but if I understand it correctly, the spectrum of the Rabi is the efficiency of depending on the wavelengths to excite, and spin's natural line width is the uncertainty in the energy level. And I don't see how that should be anything correlating in that sense, because that is just the efficiency to excite at given wavelengths. Why would that have anything to do with the amount of uncertainty of the variables?
Yeah, but
Different
don't
energy
board, right?
frequencies you can excite and excite, but it has some coordination, but I don't think it is a resonance. I believe there is some, but I don't want to go there and confuse.
Yeah, I mean,
that uncertainty will be like if it's just one, then that resonance will not be
30 seconds.
If it's very more than 50, then we have.
You mean if you're close to resonance point but not really there?
It's not only because.
I mean, it's still possible to get oscillation because of uncertainty.
That also
But when it's not even that, when we know.
yeah, I think it can certainly be some kind of correlation, but I don't think it's
it's only one.
Yeah. So you have to be correct to get the resonance going.
All right, hands up. Get back to your line, please.
But you still have to be within them to reach the resonance stage.
All right. Hey guys, stop. Okay. Anybody want to change side? Man, this is not working. Nobody's convinced of anybody. Gosh, we're wasting our time.
We're still discussing.
Okay. All right, we're gonna have second round. Okay. I guess you two can be one group and you three can be one group.
There can be a relation between
I appreciate if you guys speak English. I asked the Chinese student to do the same.
Rabi oscillation, which also has a.
What do you mean by that?
But he said if this is
This
like
also
one state,
contribute
right?
to
This is
this.
exciting
If
state.
there is
And
degree
it go like
and all those things
like this is when we have a little bit of
but it has some proportionality.
we sometimes end up here and here when we are not in the natural language, right?
What do you mean by here and here?
Like you don't end up exactly on this energy level.
Here.
Isn't that what the question is asking?
What is
The question, why is this what this question is asking about?
I think if I understand correctly, what you have painted here is the spin's natural line width, like the uncertainty
Oh yeah,
of
when natural answer.
the uncertainty or the variance of particle having ending up in this energy level. And the question is if this is exactly the same as, for example,
packet that he draw like a packet of frequency at the beginning.
efficiency
That's the frequency we are inputting the microwave to produce the frequency.
of the Rabi spectrum.
Meaning-
So if we have a frequency here, we're not exciting anything. If we're exciting a frequency here, we're exciting like the most.
This is the
Yeah, the
frequency.
maximum, yeah.
This is
But
the
what's the
microwave that
measure
we are
here? Is this the thing measure we're talking about?
Yeah,
This
I
has
think
some
this is like the variance.
what's
that is
contained in this also
Rabi spectrum.
will affect the spectrum. Like if there is
But what
tuning
sets the limit?
inside that,
Like
that
half,
will affect.
which half maximum or?
The variance is
Oh, it's just the variance
what I-
measure, I guess.
yeah.
But the
Or
other
I
thing
think you
also
can
has a
see
parting.
this as the same
It's not
distribution
equal.
as
Something
we
from
can
this
see
part will also.
in the uncertainty here.
Oh, yeah.
1 minute.
Example.
The question is if these two are the same. I guess.
Yeah.
This is determined by the structure of the entry center.
Yeah.
This is determined by
Attack. Challenge.
it's determined by
And we have a
when we reach oscillation or not, right?
Is also
But I don't see any correlation between this distribution and the uncertainty in energy.
yeah, this is like proportional.
yes. So I
Meaning
call
if
this
you have
one
to
is,
I don't understand what this is still. This is just
so I call
So for example, if we have the microwave
Yeah.
in a certain frequency,
This is microwave frequency. And this is what?
He's saying
the
natural
y-axis is,
because
for example,
microwave
the
when we are doing
efficiency
the
of
width in the
excitation.
Okay, it's just
So-
efficiency of
Yeah. Here we excite everything, where we have the frequency way up, we're not exciting anything.
But this one you can
Exciting is
change.
oscillating,
Yeah, this
right?
one we can change and with that change the
Because we
frequency
are
also
like
change.
Rabi, we're not in general excitation.
Frequency.
That depends on what you meant by picture. What I understand is that this is the distribution that we saw, for example, in the Lab2.
Okay,
Equal to
yeah,
natural
yeah.
width, every time we will get the same for the same.
It is quite useless.
But the only way to get excitation is if we end up here.
I think that's
Why
why
wouldn't
it's
this be a
more
copy?
referred to,
More excitation if you're more likely to end up in the middle.
Right. It's like
But if your light wave is a bit off, like here, your frequency from the microwave,
Yep.
you end up a little bit out here.
Why?
30 seconds.
Wrong frequency
Yeah.
is right frequency exactly on the line here, right?
Also,
Yeah.
So if frequency is a bit off,
It's a spectral
then
line.
you're going to be a bit off from a line.
Right? Say if I have
No.
half
Sorry.
of the efficiency,
Not only this.
here,
No.
I wouldn't say it's a predictive. It's
It's
quantized.
always
You
in
can
the
only have
same.
either up here or down there.
Yeah, but it's probability. Because you still get something here, like at this point. You're not really on the line, but you still get it because it's certain things. So the question is if the shape is the same.
What are you doing?
I have idea.
I mean, I can
Then
see
then
how
convince other people you're right.
is different energies on the x-axis.
Should I bring you a chair and just like sit there and think? Engage, engage, attack.
I think it's correlated, absolutely, but I don't see how it should be exactly the same.
Interrupt. You guys are wrong.
It should be like this. Just this one. And this
I see your point. It doesn't have to be a pure copy. It could also be a pure copy, or why couldn't it be a pure copy?
Oscillation
We're
inside
measuring
the microwave. It's not
But
until
efficiency is basically
But
how
this will also
you
change the language.
actually get an allowable excitation. And up here, that's the most allowable. If you go a little bit higher, but yeah, it doesn't have to.
Yeah, but I think when we change the microwave.
All right, thumbs up. Hands up. All right. Okay, go back to your line. I like that. Thank you very much. That's the attitude I like. Okay. Okay, go back to your line. Anybody want to switch position? Yes or no? How many remain in your initial position? Raise your hand. You're all in your. Okay. All right. So let me just briefly explain how this works. You first start with you are wrong. Okay, let's all say you're wrong. Can you say you're wrong? Say you are wrong.
I think we establish a
No.
common basis first
No,
of an
no.
understanding of
No,
the
no, no,
problem.
no. It's not like, oh, we are trying to work out a solution as a team. No. This is not how it works. This is not a company meeting. We're scientists, okay? And we're trying to do scientific debate here. And we're using this as a tool to learn. So the first thing you do is, you're wrong. Okay? Say, you're wrong. Can you say, you're wrong? Say it. You are wrong. I want to hear these 3 words every time when we do the discussion. Okay? Can you say you are wrong, please? You're wrong?
Yeah, he's probably wrong.
No, say you are wrong.
You
say
are
it to-
wrong.
yeah.
You are wrong.
Good.
You are wrong.
Okay, say it to me.
You're wrong.
Good. Very good. Start with that statement. You're wrong. Okay? And then you let the person explain why he thinks he's right. And then you continue to attack why he is wrong. The purpose of this is to gather information for yourself. Through the debate, okay? You can gather information for yourself, not a shared knowledge. Gather information for yourself. Through the debate, you can like try to see maybe there's a logic flaw in your thinking, or maybe there's a logic flaw in the other person's thinking. Maybe he's thinking about the same thing as you think. But when you challenge him, it's the same as you are challenging yourself. Okay? So you're gathering information. It doesn't matter if you finish your discussion before the time, before the 2 minutes or not. You're in every encounter, you're gathering information for yourself. And then finally, you need to make a decision for yourself. What is right and what you think is probably right and probably wrong. Okay? So that's how this works. That's how this time that we spend about already 20 minutes in this. Okay? If we're not doing this right, then this has no use, and we are wasting our experiment time. Okay, so please, let's next time we start with you're wrong, and then we do the discussion. Okay, so it's the resonance spin. The answer is no. The answer is no, unless your Rabi pulse length is more than 1 millisecond. And even if in that case, the coherence time will kill the Rabi oscillation, so it's no use anyway. So in the practical situation, the answer is no. So we have Vida and Musfa. Congratulations. All right, let's go move to the lab. In my lecture, in the coherence lecture, I will explain how this works in more detail. Okay, but I hope this is a good start for you. All right, thank you, and thank you for participation. And let's go to the lab and do the experiment.
You mean the spontaneous decay is still not like overcome the Rabi? You mean because Rabi is just like happen in a short time there.
If Rabi can be very long, right? What's the line with? You heard about transient broadening, right? Transient broadening. Okay, so this is omega 0. This is omega 0, right? But none of them are infinitely long. If they are infinitely long, then the spectrum of the microwave is indeed omega 0. But since they are not infinitely long, the Fourier transformation will determine their width. Okay, so the width of this. This is just the field, the spectrum of the field. Okay, so the field contains this much frequency components if the pulse is short, and if the pulse gets long, then this width will go shorter. This is just Fourier transform, and this is called transient broadening. Okay, and I'm not talking about Paul broadening yet, but this alone will enough to broaden your pulse because this is usually 100 nanosecond. Okay, so if you do a Fourier transform, basically just that. Okay, you'll get about, so say, a 10 megahertz width. Okay, so this is a 10 megahertz width, a spectra component in the field. Okay, so when you have a two-level system and the resonance is here, right? When you scan the central frequency, which carries this big width, yeah, when you're about 10 megahertz detuned, you can already make the excitation because the tail, you have a frequency component touching the excitation frequency, resonance frequency, right? So when you scan this across, this will have a width identical if we neglect power broadening. This will have a width identical to this width. The natural line width of this is 1/1 millisecond, so that is 1 kilohertz. Okay, so see, this is for the magnitude smaller. So unless you have a very long pulse, which limits your frequency bandwidth to 1 kilohertz or even under, then you can see the natural line width. Okay, yeah, all right.